Today we'll look at some ways of quantifying what are the chances of given some different scenarios. Abraham Lincoln said that the probability that we may fail in the struggle ought not to deter us from the support of a cause we believe to be just. Our study of statistics is just and worthwhile, and probability, though it's a little bit of a conceptual departure from what we've been doing, is going to be this brief foundation we'll get for probability is going to be a very useful tool in the furthering the rest of our just cause for studying statistics, and hopefully for helping you in the future support causes that you believe to be just vis-a-vis an informed perspective. It's important to note that we just are looking at one model for probability here, and it's called the frequency interpretation of chance. There's other ways to quantify probability. Probability itself is its own big field. There's whole classes and textbooks on the subject, so we're just doing a very brief overview. In that vein, I'm going to highlight for you some important points about probability and finding the chances given some specific scenarios that we in our next unit are going to apply in the context of various research related examples. So this is just some groundwork for the next stage that we're going to, but we need to know some basic rules of probability and the terminology and some minor applications. The first thing to keep in mind is that chance is just the percentage of time that an event is expected to happen given repeated sampling that is independent and under the same conditions. And this is a really important point that you should keep in mind all throughout thinking about probability now, and also when we look in our next several units or next several chapters, we'll be looking at some applications of probability to the normal approximation and to sampling. And this is a key point here. We'll be looking at repeated sampling that's independent, but under the same conditions, as in with the same population. Chances are always between 0 and 100%, just like the probability itself. The proportion would be probabilities are always between 0 and 1. This may seem obvious, but it's helpful when you're thinking about more complex chances and maybe in sometimes multiple events to remember that the chance of something equals 100% minus the chance of the opposite thing happening. And so this framing might be useful to us in looking at some of the problems and applications we're going to examine. Generally speaking, the probability tells us the number of favorable or target outcomes we're interested in out of the total possible number of outcomes. But there's some nuance to how we break down those events, and we'll look at that in just a moment, a couple of ways of classifying events. But first, let's think about this idea of drawing at random from a box, because this example of drawing at random from a box is used at many points during the discussion of probability. So it's important that we have a clear idea of what's happening here. And it's a nice model for just some general ideas in thinking about sampling, which is that it's either sampling or drawing in terms of this box, sampling with replacement or without replacement. So when we have sampling with replacement, we take the first draw, as you can see, number 3 comes out of the box on the first draw. If there is replacement, then a different 3 is put back into the box, so that your second draw could still be any of these options, 1, 2, 3. But without replacement, we would then have a smaller number of possible numbers to choose in our second draw, the without replacement. We could only at that point get a 1 or a 2. And we'll break down this with replacement and without replacement in terms of some of the terminology and rules for handling probability. So let's keep that in mind, but think quickly through just eyeballing some of these probabilities or these chances that they've given us in our numerical answers, because it's important, most important here, to remember that for A, for example, this can't be right. An important thing you should take away from our whole course is recognizing when something is clearly wrong because the data are outside of the possible options for this measure. And in this case, if a chance can only be from 0 to 100, of course, a negative 50%, obviously there's a bug in the program. 0% is possible. That means this event won't happen. It never happens. So 3, a 0% chance. It just never happens that way. We can then move up these measures, these gradations of chance. We're at 10%. Something may happen, but it's not likely. This is extremely unlikely, a 10% chance of something happening. 50% chance. This is, we're already familiar with 50-50 odds, probably. It's as likely to happen as it is not to happen, or 1 here. 90% chance thing is very likely to happen. This means 9 times out of 10 times this event happens. A chance that's equal to 100% happens all of the time. Anytime you encounter this scenario, the event always happens. And again, 200% is another example of there's clearly a bug in the program or there's a problem with the reasoning, because any percent that is over 100% in terms of a chance is not valid. A couple of other estimations. A coin will be tossed 1,000 times. About how many heads are expected? Well, we know that heads come up 1 out of every 2 flips of a coin on average. So about how many heads? About 500. Because we can take the chance of getting a head on any particular roll and just, these are all independent events. We can look at our 1,000 times and we know it's going to show up 500, more or less. We can apply the same logic to thinking about a die, but we're going to look at some more of these probability calculations in a moment. Okay. But the first general rule or idea we need to consider when we're looking at our probabilities and events is this idea of it being conditional. A conditional probability is the probability of an event given that another specific event has occurred. So you can only, the second event depends on the first event happening. Or maybe it doesn't depend on the first event happening, but the condition of the probability, you're looking at 2 events, the condition of it happening is that event A happened already. So we need to examine, in the context that A happened, the chance that B happened. Let's simplify this for a minute and just look at this example. A deck of cards is shuffled, and the top two cards are put on a table face down. It's important to remember we can consider a deck of shuffled cards to be in a random assortment pattern, and you win $1 if the second card is the Queen of Hearts. So what's your chance of winning the dollar? Well, there's always a 1 out of 52 chance of getting the Queen of Hearts, because the Queen of Hearts is one card out of a total number of cards, 52. It only occurs the one time, and there's an equal probability of getting the Queen of Hearts in any particular card. But now we have a special scenario where in part B, you turn over the first card and it's the 7 of clubs. So now what's your chance of winning, given that the 7 of clubs is the first card? In this case, we've got a conditional probability. The condition is the 7 of clubs is the first card. And so now the probability is 1 out of 52. We know, or excuse me, 1 out of 51, sorry. Why is it 51? Because we already know that one of the cards that's remaining in the deck, we've already taken out one card. That card is the 7 of clubs. We know it's not the Queen of Hearts, so it's not available in our set of remaining cards. There's 51 cards remaining for this in the second card, and one of them is not improving. One of them is the Queen of Hearts. So the probability is 1 out of 51. And just to help reinforce the idea here about the conditional probabilities, this one, scenario A, is called an unconditional probability, whereas the part B represents a basic conditional probability. And then we're presented with the multiplication rule. The multiplication rule enables us to get the chance that two things will happen, both will happen, and it equals the chance that the first will happen multiplied the chance, sorry, a little tongue-tied here. The multiplication rule tells us that the chance that two things both happen, two separate events both happen, is equal to the chance that of the first happening multiplied by the chance of the second happening, given that the first happened. This maybe sounds similar to what we were just talking about, but we are going to add in another little wrinkle in terms of thinking next about independent and dependent events. But this is just another wrinkle in the probability rules. So we would be here, we're just saying that the chance that two things will both happen equals the chance that the first will happen multiplied by the conditional chance that the second one will happen. It's also true that if two things are independent, the chance that both will happen is the product of their unconditional probabilities. So if that idea is tricking you up a little bit, that's just a special case of the multiplication rule, but you shouldn't worry about it too much in the context of our class. It is important to remember that you need to check for independence of events, though, or just use conditional probabilities. Because if you blindly multiply unconditional probabilities, then you can get real trouble in terms of heavily elevated probabilities that go way beyond what is actually even possible. And so as an example, based off of the previous example we looked at, you can see that this is the same scenario. And first probability here, the 1 out of 52, it's the same scenario, but we've got the chance that the first card will be the 7 of clubs. That's 1 out of 52. The chance that the first card is any particular card is always 1 out of 52. And the chance the second card will be the Queen of Hearts is 1 out of 51. But then we, instead of looking at both of these separately, quiet. Yes, quiet. So when we look at these two together, we, given that we need to know what's the chance of getting both the 7 of clubs on our first card and the Queen of Hearts in the second, is going to be equal to the chance, the multiplicative chance of the two probabilities together, or a very small chance that works out to about 1%. And our final topic is this idea of independent events. So let's think about, we've already discussed this a little bit. When we have independent events, the chances for the second given the first are the same, no matter how the first event turns out, because the events always occur independently. A great example of independent events are coin tosses. We all know that each time you toss a coin, there's an equal chance of getting heads or tails. It doesn't matter what you got on the previous toss of the coin. It has absolutely no relationship to the probability of getting a heads or tails on the next toss of the coin. And it's the same when you look at dice. Each throw of the die is independent. And there's lots of great examples, as I'm sure you can tell already, of applying these ideas in the context of games and gambling. That's a fun way to practice some of this if you are if you like to gamble, or if you'd like to gamble with more success. We see both independent events in games like this, like roulette. Again, it's independent. Each throw of the ball is an independent toss. Dependent events, however, are different. The chance of the second event then depends on the outcome of the first event. So given that the first event had a specific outcome, then we can figure the probability of the second event. And this is just the idea of independent and dependent events. And we're going to use this more in some later applications in our next units. But it's important to get this idea down, that events can either be found to be dependent or independent. And when you think about it, drawing at random with replacement, and we cast this into the most simple model possible. If you draw at random with replacement, each draw is independent, because each time you draw, you have the same outcomes available. Without replacement, the draws are dependent on each other. So given that you drew 3 on your first draw, then what's the probability of you getting 1 or 2 on the second draw? Because there's a smaller number of events available. And you're specifically looking at the scenario where you had a particular outcome in the first event. In our next section, we'll look at some of the review exercises for probability. In summary, the important issues of probability to keep in mind are these ways of thinking about events. Events as being conditional or unconditional, independent or dependent, and we looked at the multiplication rule for getting the conditional chance of events happening. In chapter 14, in that little portion of chapter 14 that we look at, we're going to look at one more rule, the addition rule, which is for another one more context for probability events. And so we'll just look at some simple applications of these items in our next section.